Hello everyone. For today's video lecture, we're going to be talking about particle collisions in 2 dimensions. So, collisions and impulse, going back to review a little bit of this. One instance in which the impulse momentum equations are particularly useful is when we have bodies colliding. So when we have this collision between 2 bodies and it occurs fairly quickly, which is most kind of rigid collisions, we're going to have a system of particles and we're going to analyze that system as a whole. So we have one impulse momentum equation that we use as our starting point. And the reason we do that is because internal impulses, those are the impulses exerted between bodies that are colliding, are going to cancel each other out because of Newton's third law. Those forces must be equal and opposite, and the times are going to be the same. So the impulses, you're going to have one impulse in one direction, another impulse in another direction, and they're always going to cancel each other out. That way we get to ignore the very large and very quick forces of the collision for our equations. So external impulses are also generally going to be negligible because of the very short time frame. So all these collisions happen within milliseconds for rigid bodies. And so the forces are very large and they're going to kind of dwarf any external forces on the bodies except for those collision forces. So that's why we use impulse momentum equations for collisions here. All right, so conservation of momentum in 2D stems from the fact that if we have no external impulse, we have no change in momentum. So our original equation for the conservation of momentum that we built up in the 1D version of this lecture was this. So the final momentum of particle A plus the final momentum of particle B is going to be equal to the initial momentum of particle A plus the initial momentum of particle B. So momentum is conserved before and after the collision for the system as a whole. All right, so in a 2D system, we break these down into components. So here I've broken them down into X and Y components. And so that's just I've taken the same equation I have above, and I've just put X and Y in each of the subscripts here. So we're getting a bit of a kind of soup of subscripts down here, but just to walk through it real quickly. So we've got 3 pieces in all these subscripts. The first piece is particle A, particle B. So which particle is it dealing with? The second part is final or initial. And so this is the final velocity. This is the initial velocity over here. And the last part is the direction. So X and Y are my 2 directions in this point. So body, initial or final, and then coordinate direction. All right, so there's 2 conservation of momentum equations. But those usually aren't going to be enough. So we want to supplement our conservation of momentum equations with something else. So to be able to solve for 2 unknowns is usually not enough. We're going to need usually 4 equations actually to solve for all the unknowns. And the reason we need 4 equations in many cases is if we have all of our initial velocities and we want to solve for all our final velocities, we actually are going to have 4 unknowns. We're going to have 2 component direction velocities in the final state for particle A, and then another 2 for particle B. And so each particle has 2 directions for the final state, so we're going to have 4 unknowns generally. All right, so the other equations we're going to use to supplement this, so we need at least 2 more equations, are going to be built up depending on the type of collision. So conservation of momentum is going to be used regardless, but the other equations are going to vary. All right, so the type of collisions, just as a review, going from kind of our perfect bounce to no bounce at all, with some bounce in the middle. At the top end, for a perfect bounce, we've got a elastic collision. So this is where it's basically billiard balls are very close to an elastic collision. And it's where 100% of the kinetic energy is conserved. So after they bounce off of one another, they don't lose any energy. On the other end of the spectrum, we've got inelastic collisions, where the bodies stick together after colliding. So if these 2 bodies come together and they just stick together, the velocities of the 2 bodies can be the same after the collision. That's what we're going to use there. This is the lowest amount of kinetic energy that can be conserved. So some is still usually conserved. The 2 bodies are going to move away unless you kind of perfectly match up the velocities. But it's the least efficient type of collision. And then semielastic collisions are somewhere in the middle. So we're going to lose some of that kinetic energy in the bounce, but they're not going to stick together. So what we need there is the coefficient of restitution to relate the velocities before and after collision. All right, so inelastic collisions is the easiest place to start for this. So because the bodies in inelastic collisions stick together, post-impact, the final velocities of both bodies are going to be the same. So both components, the x and the y velocities in the final state, are both going to be the same for particle A and particle B. All right, so combining this with the conservation of momentum equations, kind of simplifying the results, leads to the following equations. So that's the x direction, and this is the y direction. So I've got the combined mass and the final velocity. And remember, there's no separate A and B. They are stuck together, and so they're going to have the same final velocity. So combined mass and final velocity in the x direction. And this is the initial momentum of each particle in the x direction. So initial momentum of particle A in the x direction, initial momentum of particle B in the x direction. All right, same thing except y direction down here. So combined mass, the final velocity in the y direction, and the initial momentum in the y, initial momentum for particle A, initial momentum for particle B in the y as well. So inelastic equation, we can use any coordinate system so long as we're consistent. We just kind of replace the x and y with whatever coordinate system we want. All right, so that's the equations we're going to use there. We've kind of built two equations here. We reduced our number of unknowns by saying, oh, okay, they stick together. So these are just one variable down here. All right, elastic and semi-elastic collisions are going to be a little more complicated. So for both elastic and semi-elastic collisions, we're going to use the same strategy. So we're going to use the coefficient of restitution rather than conservation of energy. And we're going to do that because it makes our life easier. It's going to be easier algebra to deal with. All right, so the strategy relies on using a specific coordinate system as well. So we want to use the normal and tangential coordinate system. We want to make sure we label these in the diagram and break down any velocities into normal and tangential components. So if we have two bodies colliding, like with these two billiard balls right here, the plane of contact is the kind of plane along which they're going to be impacting. And if you think about the normal forces of the impact, those would be perpendicular to that plane of contact. So the tangential direction is going to be along the plane of contact. The normal direction is going to be perpendicular to the plane of contact, like I've got drawn here. So those are our coordinate directions, and we need to make sure we stick to those coordinate directions, not just any old coordinate direction. All right, so if we use these coordinates, we can generate four possible equations. The first is just the conservation of momentum in the normal direction for the system. So this looks like what we had for x and y, except it's in the normal direction. So final momentum of particle A in the n direction plus the final momentum of particle B in the n direction is equal to the initial momentum of particle A in the n direction plus the initial momentum of particle B in the n direction. All right, so that's equation number one. Equation number two, so rather than doing the same thing in the tangential direction, we're going to notice something specific. So all of our forces, by definition, are going to be in the n direction, which means that there's no forces on either particle in the t direction. When we have that, there's no change in momentum. So no impulse, no change in momentum. As long as our mass isn't changing, which most of the time it's not, that means the velocity in the tangential direction for either particle is not going to change. So the velocity of particle A final in the tangential direction is just equal to the initial velocity for particle A in the tangential direction. And same thing for particle B. So the velocity in the tangential direction for either particle does not change. All right, so now we've got three equations because I've got these very simple relationships for the tangential direction. All right, so last equation in here, we're going to use the definition of the coefficient of restitution, which relates velocities in the normal direction. So we had this for semi-elastic collisions before. And so this is the piece that we had before. And this is some combination of what we did in 1D particle collisions, as well as what we did for the surface collisions, where it's only the normal component at play here. So this is the coefficient of restitution, which hopefully we are either given or going to be solving for, is going to be equal to the velocity of particle A, final in the normal direction, minus the velocity of particle B, final in the normal direction, over the velocity of particle A, initial in the normal direction, minus the velocity of particle B, initial in the normal direction. All right, so for elastic collisions, we just need to set E equal to 1. And then for every semielastic equation or collision, it's going to be E is some number between 0 and 1. All right, so with that, we pull it all together. We've got 4 equations. We can solve for up to 4 unknowns. Usually, it's going to be the 4 final velocities. So particle A, normal, particle A, tangential, particle B, tangential, particle B, normal. Where's that one? This one here. So we've got all these variables, we put them all together, we do a lot of algebra and solve for the results. All right, so the process, just to review, solving these collision problems involves 3 steps, carefully accounting for the factors at play. So set up a diagram. Show the initial and final velocities of the 2 particles before and after the impact. Some of these things are going to be known, some of them are not going to be known. Identify any known or unknown velocities in each state. Try to break it down into components. Identify the type of collision and the coefficient of restitution if applicable, and label the normal and tangential directions for all elastic and semielastic collisions. So once we've got our diagram set up, we go ahead and put together our equations. So we're going to need to put together the conservation of momentum equation or equations, along with the other appropriate equations for the collision type. So we had some for inelastic and then some for semielastic or elastic equations. So you need to break all of our velocities down into component directions, which involves a lot of sines and cosines. And then step 3 is just solve the equations for unknown quantities. So once we have all our equations set up, we're going to go ahead and do the algebra, solve for the unknowns. All right, so with that, that's all I have for today's video lecture. Thank you for watching, and I hope to see you again.